Hi, thanks for joining me today. I've got a fun problem involving integrals. So let a and b be real numbers with a strictly less than b, and let f be a continuous function defined on the closed interval ab to the reals, such that the integral from a to b of f of x times x to the n dx equals 0 for all natural numbers n, and also when n is 0. Okay, so f of x is a continuous real function defined on the closed interval ab, and it has the property that no matter which natural number n no matter which non-negative integer n you choose, the integral from a to b of f of x times x to the n dx equals 0. We want to prove that f of x is identically 0. Okay, so of course if f is identically 0, then clearly this is true, but we want to show that the converse holds. So given that this is true, it follows that f is identically 0. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to get stuck into a solution. Okay, so to solve this problem, we're going to be using what's known as the Stone-Weierstrass theorem. Now, actually, what we're going to use is just like a corollary of the theorem, so something we can deduce from the theorem quite easily, and that's all we need for today's video. Okay, so I've written down what we need here. It says that for all natural numbers n, there exists a polynomial Pn of x such that the magnitude of f of x minus Pn of x is less than or equal to 1 over n for every x in AB. Okay, so in other words, no matter how big n is, so even if you give me a really big n, I can find there exists some polynomial Pn of x such that f of x minus Pn of x, the magnitude of that is really small, so in other words, Pn of x is a really good approximation to f of x. Okay, so I'm not going to prove this theorem, I'm just going to state it, but it's going to be really useful and it's going to help us solve today's problem. And now I've written a claim here. For any polynomial p of x, the integral from a to b of f of x times p of x dx equals 0. Okay, and the proof of this is not too difficult, so let p of x be a polynomial, then I can write p of x equals the sum from I equals 0 to some capital N, say, of alpha I times x to the I. Okay, so obviously p is a polynomial, so I can write it in this form. Okay, so now this integral here becomes the integral from a to b of f of x times the sum from I equals 0 to n of alpha I times x to the I dx. Okay, but I can swap the summation and the integral, so this thing here simply becomes the sum from I equals 0 to n of alpha I times the integral from a to b. Oh, that's an awful b. That's an even awfuler b. The integral from a to b of f of x times x to the I dx. But remember, by assumption, this thing here is always 0. So we've just got the sum from I equals 0 to n of alpha I times 0. So of course this thing here is just 0. Okay, now what we're going to do is combine these two results to get the desired result. In other words, prove that f is identically 0. Okay, so how I'm going to prove that f is identically 0 is I'm going to start off with the integral from a to b of f of x all squared dx, which is, I've just written as f squared of x. So that just means f of x all squared. So I want to show that this integral here is 0, and then using sort of an analysis type argument, noting that f squared is a non-negative function, it must follow that f squared is identically 0, and thus f is identically 0. Okay, so the integral from a to b of f squared of x dx, well, this here is going to be the same thing as the integral of f squared x dx minus the integral from a to b of f of x times Pn of x dx, where Pn is sort of the polynomials I had before, and this thing is the same as this thing, and this thing is just 0. So this thing equals this thing. Now bringing everything under one integral, this is equal to the integral from a to b. I can factor out 1 f of x, then that's f of x minus Pn of x dx. Okay, so we get the integral from a to b of f squared of x dx is equal to this guy here. Okay, now what I want to do is take magnitudes of everything, so this thing here is equal to the magnitude of this thing here. It's also equal to the magnitude of this thing here. Okay, but now we can sort of use the triangle inequality on integrals and show that this thing here is less than or equal to the integral from a to b of the magnitude of f of x times the magnitude of f of x minus Pn of x dx. But remember, we have this thing here is less than or equal to 1 over n. Okay, so this thing here is less than or equal to, we can bring the 1 over n to the front, the integral from a to b of f of x dx. Okay, the integral from a to b of the magnitude of f of x dx is just some number. Okay, and I guess one thing to note is because f is continuous on the closed bounded interval, this is indeed a finite number. It's not going to tend to infinity or anything like that. So this is a nice bounded constant number, and we're dividing by n. But this holds for any n, and in particular any arbitrary large n. So taking the limit as n goes to infinity on this side and this side, of course this thing here goes to 0. So we have that the magnitude of the integral from a to b of f squared of x dx also tends to 0. So it follows that the integral from a to b of f squared of x dx equals 0. And now that must mean that f is identically 0 because f is continuous, so in particular f squared is continuous, and also f squared is non-negative. Okay, and the integral of a non-negative continuous function, if the integral of a non-negative continuous function is 0, then it follows that the function itself must identically be 0. And I guess one thing to point out is the continuity argument is really important, because if we had f squared wasn't continuous, then it could be that f is not identically 0, and an example of that is if f is 0 everywhere except at one point where it's 1. But yeah, that's just a small technicality. So we have that f squared must identically be 0, and thus f is identically 0, and we're done. Okay, that's the end of the proof. Okay, yeah, so that solves the problem. I hope you have enjoyed this video. I guess the main bit to this theorem was, the proof was knowing the Stone-Weierstrass theorem, and then from that, this is quite a cool argument. You're looking at the integral of f squared dx, and you show it that it's 0. And that's something you do a lot of the time in maths. When you want to show that a quantity or a function is identically 0, you take the integral of its square and show that that's 0, and using continuity, it follows that the function itself must identically be 0. Anyway, I hope you have enjoyed this video. If you are new here, please do consider subscribing and checking out some of my other fun maths videos as well. But that's all for now. I will catch you in the next one. Have a great day.